Okay, so let us continue our discussion with this next definition, the definition of a dual space. I mean, the name of this section itself is dual spaces, but now only we are going to define dual space. Definition: if V is a vector space over some field F, then the dual space of V is this space, home V, F. We already know what this is. We mentioned this before also. In fact, let us just briefly go through what we have done so far. Let's just have a quick summary. In this section, we are considering linear transformations on vector spaces or vector space homomorphisms from one space to another. And in particular, we are not just considering one or two linear transformations. We are not studying individual linear transformations, but rather their collection. If we have two vector spaces V and W, where the underlying field of scalars, they have the same field, okay, say F, then we have considered the set of all vector space homomorphisms from V into W, and we have introduced an addition and a multiplication by scalars on this set itself that turns it into a vector space. And we have also calculated the dimension of this space when V and W are both finite dimensional. We have already seen these things, and towards the end of that discussion we mentioned something. We mentioned two special cases of this. One of them is of course this, where the two spaces involved are the same. When we mentioned this, we said that besides the vector space structure, one can define a kind of multiplication on this set. Like you can take two linear transformations or two homomorphisms and you can multiply them. That multiplication of course is function composition. Now what that does is that with that multiplication as multiplication and with the vector space addition which is already there in this structure as addition, this becomes a ring. And something else is also true. Another additional axiom is true, property is true, that links this multiplication that we are saying we can define on this set and multiplication by scalar. So this entire structure then is called an algebra, and a study of this thing is known as linear algebra. We will do this towards the end of this. In chapter 6 we will do it. So this is one case, and the other case is this. Where the second space is the underlying field of scalars itself. We know that F is a vector space over F, so this case can also be considered, and considering this case, in fact, it will turn out that we will get many things, okay, quite a few things we will get. One of the one of the applications of the results that we will get by considering this is in the solution of a system of linear equations. Okay, we will see these things. So now we are starting off with this definition. If V is a vector space over F, then this space is called the dual space of V. We will denote But of course we won't keep on writing a cumbersome notation like this. We will devise a shorter notation to denote the dual space of V. We will denote the dual space of V by this notation, V hat. Okay, because the underlying field is understood, so we do not include that in this definition, saving space. We just simply write V hat. The elements of V hat will be called linear functionals. Functionals of V into F. Because if you think about it, what are the elements of V hat? The elements of V hat means just this. So any element in this is just a linear transformation from V into F. It's a special kind of linear transformation where your inputs are vectors and the outputs are scalars. Okay, so they are called linear functionals of V into F. Now, if your original space V is not finite dimensional, if it is infinite dimensional, then the entirety of this home V comma F is far too large to be of any interest. That's what the author is next discussing. If V is infinite dimensional, then V hat is far too large to be of any interest. In this case, we usually impose some additional structure such as a topology on the space, and as the dual space one does not usually take all of your all of the space, but rather a properly restricted subspace. Okay, so what the author is saying in this part is that if our original space V is infinite dimensional, then the dual space is extremely large to be of any interest. I mean, it has so many different types of things that you don't get any general result, something like that. And in this case, what we usually do is that besides the vector space structure, we also impose some additional structure such as topology, which somehow in some sense is compatible with the vector space structure. If you have already gone through even a little functional analysis, you may have already come across, not just may have, you must have already come across these types of spaces which are topological vector spaces. Examples of important such spaces are Banach spaces, Hilbert spaces, where you not only have the vector space structure, but somehow there is a topology also, which is, the two structures are linked in a very natural manner. For example, in a Banach space, if you recall, is a normed linear space. Okay, there you have a norm, and from that norm, a metric structure arises, and from that, of course, you have a metric topology, and the space is complete also, those things are there. And in a Hilbert space, on the other hand, we take one step back, and from there we start. It's an inner product space. From the inner product you get a norm, from the norm you get a metric, and from the metric you get a metric topology. So those things are there. And in such cases, what the author is saying is that we do not usually take the entirety of this space, but rather a properly restricted subspace. In some sense, an important subspace where we believe that with this additional structure we will get some interesting result, and we will not get lost in these extremely large spaces. So that's why this type of restrictions are also taken. But we are not going to study those things. For us, mostly we will be considering only finite dimensional vector spaces V, so that our V hat in fact is the entirety of home V comma F. So that also the author mentions next. The amazing thing about these things is that they look very abstract. Within mathematics also, if you think about it, they look very abstract. And they are beautiful, no doubt. So they should be studied in their own right, but at the same time they are highly applicable also, because these things appear everywhere in the theory of differential equations and everywhere. In fact, we will see all those things when the time comes. If, however, V is finite dimensional, then V hat is, of course, the author has written some language as we did it. I don't remember those things. Then V hat is, of course, the entire home V comma F. That means for us V hat is just this. Whether finite dimensional or infinite dimensional, our definition says that V hat is this, and this is what we are calling the dual space of V. Infinite dimensional case we are not going to consider. We will consider only finite dimensional vector spaces, of which we will consider duals. However, you can of course if you are not able to immediately recall any infinite dimensional space, you can always take this, the space of polynomials over any field. This is an infinite dimensional vector space. There are others also, but this is a particularly easy one because we have already seen this. Okay. Now what we do, now we turn to the finite dimensional case and let us see what the thing here is. I mean, we are actually still considering a home space, right? But in particular, we are now considering the second space to be the scalar field itself. So, do we get anything new from this special situation? That's what we want to see. And of course, we are helped by finite dimensionality of V. Let V be an n-dimensional vector space over some field F. So there will be some basis having n elements. So we consider one such basis, V1, V2, etc., Vn be a basis of V over F. Okay. Now we define functions V1 hat, V2 hat, like that, Vn hat. These are functions, okay, from, that means for each basis vector we are defining a function. Now we will say what the functions are. From V into F given by Vi Vj hat equal to, because we are saying we are defining, so let me just use this colon. It means the definition. The meaning of this is equal to 1 if I is equal to j, and this is defined to be equal to 0 if I is not equal to j. So I hope you understand that defining a function from V into F by only mentioning or by only defining what the function does to the basis elements is enough, because then you can extend these functions linearly on the entirety of your vector space V, and by that we just simply mean this. So that means applying Vj hat on this general element of the vector space, Vj hat is equal to alpha j. Okay, then one can show that Vj hat is in fact a linear functional for each j. And in fact, we don't even have to show anything. We have already discussed these things. Note that these Vj hats are okay. To draw the and okay, let me just first write and then I will see. Are nothing but the homomorphisms Tij introduced in the proof of our theorem where we calculated the dimension of the home space. And as usual, I don't recall the number. Theorem 431. 431, yes. But how? Let's see that. And I think for that, to see how, I need to change the indices a little bit. But we will see. Okay, let us just try to draw the analogy. Analogy means it's not simply an analogy. I mean, what we are saying is that these Tijs are actually, they will reduce to these Vj hats in this special case. That's what we are saying. So for that, we quickly recall what we had in this thing. We had this, no? Phi was a finite dimensional, say an n-dimensional vector space which has a basis with these vectors v1, v2 up to vn. W also is a finite dimensional vector space and m-dimensional vector space which also has some basis. Wm. Okay. Now, what we did in the proof of this is that using these bases, we defined some linear transformations or homomorphisms from V into W in this way. For all the i's varying from 1 through n and all the j's varying from 1 through m, we define these functions from V to W, and the definition was this. If you apply it, because you are going to apply this Tij on any element of V, so as we what we did here, it's enough to only define what Tij does to each of these basis vectors. So we had our definition like this. Let me write it below here centrally. Phi k Tij, the image of Vk, the basis vector. Vk is any vector from here, from this basis, is equal to Vj if k is equal to I, or probably I should write I equal to k, same thing, but because I is varying, so that way I am writing. If I turns out to be equal to k, then by definition this image is Vj, and if I is not equal to k, then it is defined to be equal to 0. And then we proved that these Tij's, there are m number of them, we already saw these things. These Tij's form a basis for our home space. Okay, that's what we did in theorem 431. Now in this special case, here V, of course we have V again, so this is our special case. We again have V, and we again have chosen some basis of V, but now in place of this second space we have F. Now we know that F is one dimensional over itself, and any non-zero field element gives you a basis having only one vector. In particular, we can take the unit element of the field, the unity of the field. So what will now happen to these Tij's if this is the situation? Now the Tij's, okay, now note one thing, that I of course is varying from 1 through n, but j is fixed, j is equal to 1. So we don't have two indices, we don't have double indices to index these linear transformations, these homomorphisms, all of them that may arise from this situation. But we need to only have one index, that is I. Okay, so let us just simply identically do whatever we did here in this case. So for the sake of seeing that this is a special case, we will put 1 in place of j, just so that we can see that we are doing the exact similar thing in this case. Ti1, now only I will vary, and what will it be? Same thing, Vk Ti1, this will be equal to Vj if I is equal to k, and 0 if, oh sorry, am I saying it correctly? No, see, I made a mistake here, that's why. It is not Vj, that does not even make sense, because this is mapping V into W, so it has to be something in the space W, it is Wj. Yeah, this is the advantage of seeing all the things in detail. If there is something wrong, it will eventually be found. So this is Wj, sorry about that. Okay, so now we have we have options here, j varies. Here however, there is only one option, j is equal to 1, so there is only W1, so that's why we have 1, and of course 0 if I is not equal to k. Okay, fine. So now, yeah, that's why I said when I wrote this that I may have to change the suffixes. Let us call this j and let us call this I. This changes absolutely nothing, but it will help us recognize the situation. This is I. This is I. I may have written Vj here, in this part, so you please make that Vi, Vi hat. if I have written vi hat here. Okay, so now what is our vi hat? You can see from this and this and this that this ti1 is nothing but vi hat, because instead of taking k, if you take j here, then you get this now. Okay, so we are just simply without using the same notation, we have decided to use some other notation. So we haven't done anything new, although we are defining something here, but those things we already have come across. And so now we know that these vj hats are not just in v hat, because v hat is your this thing. But by theorem 431 we also, or rather its proof, we also know that this vi hats in fact form a basis for this or this, that is the dual space. Okay, so there is in fact, I can just simply make it an actual part of the entire discussion. Why put it within brackets? Because anyhow I have to now say that by theorem 431 they form a basis. Hence and you note one more thing, that there are only n of them. In the original theorem 431 their number is nm, but in this case m is equal to 1, so there are only n linear functionals which will form a basis for the dual space. Hence this thing is a basis for the dual space v hat, and it has a name also. This particular basis is called the dual basis of or dual to what is the exact way of writing this? We can just write off dual basis of the basis this of the original basis with which we started of our original vector space. So you can see that when the basis for V changes, if you take another basis, correspondingly the dual basis will also change, and that is in a sense a little problematic, because you have, okay fine, you have one basis, you have chosen one basis for V, you get a dual basis, but you choose another basis, you get another dual basis. So you have to keep track of what is happening, okay, because things are changing. It's not something nice and fixed. It is nice, but it is not fixed. So the author mentions something like this. which I may have messed up the order. I think he discusses about this thing that I am now going to write, that this issue of things changing before having these things, but anyway I can write it here also. Note that in the proof of theorem 431, the basis Tij of those vectors that we constructed that basis also, just like the dual basis, because that is the general case, depends heavily on our choice of the basis for the original spaces V and W. So if there also, if we change any one of those two bases or both of them, this basis of these linear transformations Tij will also change. So that means, so what the author is trying to say here is that if something, some construction or some definition or anything depends on such a variable object, like for example this basis, and that is what we have here. No, we have defined dual basis corresponding to a given basis, but if the given basis changes, the dual basis also changes. So when we have such a definition or something that depends on a changing thing, then it's a little problematic. A more preferable situation is to be able to have a construction or something that does not depend on our choice of basis at all. Okay, such constructions or such definitions or arguments, whatever they may be, are called invariant arguments or constructions. And it's a general rule of thumb that invariant constructions are preferable to the ones that vary, that we constructed depends heavily on the choice of the basis of V and W. So this construction is not an invariant one, so it is not basis free, and because we have used this to construct a dual basis, that is also not an invariant construction. Thus, the construction of this basis of is not basis free. A basis free construct, what else is, I mean construction, okay, but what else is there? I forgot. Invariant, oh, proof, of course, proof, yes. Yeah, I don't think there is, we need to write something more about this. I mean, of course, you understand that if those two bases of the Vi's and Wj's, if we changed any one of them or both of them, then this basis will change. Okay, so this is not a basis-free construction. As a general rule, of thumb, it is preferable to have a proof or construction that is basis free or invariant. Invariant constructions are constructions are important not only for mere aesthetics but also for the fact that we don't have to be careful about how things change when we change the basis. So if we have an invariant construction or an invariant proof, then of course it looks beautiful, so that aesthetic appeal is there, but that's not the only reason for them to be considered important. You also do not have to be very careful about how you are choosing the first basis. I mean, whatever you are doing, you are going to choose a basis for the spaces that are already given to you. So if your proof or your construction is invariant, then you don't have to think about anything. You will just simply choose basis and you will do whatever you want to do and achieve whatever you want to achieve, whatever you want to construct. But if your proof or construction is not invariant, then you have to be very careful in choosing those bases. You may have to choose some special basis so that your proof or your construction works. Okay, now that we have a dual basis for any given basis of a finite dimensional vector space, let us see a consequence of that. If V is an n-dimensional vector space because the author discussed all these things even before constructing that dual basis, so he was able to continue the discussion. Here, however, there is a break because I messed the order up. So in the middle I have brought this discussion, and now again I have to write those things. Not everything, of course, just the ingredients I have to write. If V is an n-dimensional vector space over, oh, why am I starting with if? I won't be immediately saying anything now. Let V be an n-dimensional vector space over F with basis this, and let the corresponding dual basis you may of course feel that writing all these things down is not necessary, but sometimes writing the things down is necessary, because if we just listen to a speech, we may forget many things. You can of course rewind this video as many times as you like, go anywhere you like in the video and listen to what I am saying, but if you have the things in front of you, you can look at the things, then that helps. Sometimes we have to just strike a balance between this simple speech and writing the things. Let the corresponding dual basis be this. Okay. Now what we do, we choose any non-zero vector in our vector space V. Now let V not equal to 0 be any vector in V. What we are now trying to show, only using this notion of dual basis, is that then we can find a linear functional on V which if you evaluate at V, then you will get a non-zero scalar. Okay, that's what we want to now show or argue. Okay, so V is a non-zero vector in V. Then by a previous result, do you recall that you had something like this? Say you have a finite dimensional vector space V in which you consider a linearly independent set of some vectors, say Vs. This is a linearly independent set in V, and it is given that V is finite dimensional. Then a result that we already saw before in chapter, of course we are right now in chapter 4, but in the beginning of the vector space theory, that you can adjoin some additional vectors to this linearly independent set, and so that the superset that you get becomes the basis of V. In other words, put it more simply, if you are given a linearly independent set in a finite dimensional vector space V, then you can blow it up to a basis for V itself. Now that result we can apply here, and in place of this linearly independent set, we can consider this singleton set consisting of V. Because V is non-zero, this singleton set is a linearly independent set. So you can enlarge, no matter how high dimensional V is, you can supply the missing vectors and you can get a basis. And what is that result? These numbers, though, man. It is lemma 4 to 5. By lemma 4 to 5, there exists a basis Vn of V such that the first vector is our V. You may be wondering, we already have this, but this is what this is the general result. If there is a there is a confusion, no? Because I am writing the same thing using the same symbols. So let me just slightly change it. U1, Un. If the original vector space has a basis, then corresponding to it there is a dual basis. That's the fact we are not going to use in this situation. Okay. Then we have the corresponding dual basis of V hat. Now note this. Okay, so these are our linear functionals. In particular, if we apply the linear functional V1 hat on this vector V, then what is V? V is V1 hat, and that by the definition of these functions is equal to 1, the field element 1, which of course is not equal to 0. In any field, the unit element is different from the additive identity. So we have proved this result. Prove the result which we are now going to state. What have we proved? Lemma 4, 3, 2. Let V be a finite dimensional vector space over some field F. Then for any non-zero vector in V, there exists an element in the dual of V, that is, there exists a linear functional of V into F such that Vf is not equal to 0. And that is the demonstration. One more thing I want to say here is that in the text you will see the author has written f of v, which I don't like. Why I don't like that? Because this I never understood about this man Herstein. If you are following one notation for writing functions, why do you write the other one also to make things extra confusing? You just stick to one and you just follow that. So I have decided to write the thing like this, because that's what I have been doing. In the occasional cases where there are, the other notation is in use so much that even Herstein has also followed it. There, of course, I am writing the notation that we normally use. So what I am saying here is that, say for example, you have a polynomial which you normally denote like this, which of course is not a function, but it can be thought of as defining a function. It is an expression that we already know how a polynomial looks, but when we consider this as a function or as defining a function whose rule is a polynomial expression, then I am writing f of x, and there I consider x as the input. In other cases, as much as possible, I am following this notation. Okay, anyway, so we have found this small and nice result, but this will also have an application. We will see. Now there is a fact about this lemma. Note that we have used finite dimensionality to prove this lemma, but even when V is not finite dimensional, still it is true, which however we will not prove. So the author writes, lemma is true even when V is infinite dimensional. However, we do not prove this because there are two reasons he says. One is that we will not need it anywhere other than, of course, mentioning it here. And the second thing is that its proof involves some issues of logic. Some logical issues are there in the proof which we do not want to get into right now. I think that logical issue that he is talking about here is the axiom of choice. In most of the cases where infinity is involved, where you have to make infinitely many choices, the axiom of choice is a logical issue. So anyway, we won't have to think about it. We do not prove this because we don't need it, and also because its proof involves some logical issues that we don't want to get into. Those logical issues can be addressed, but we need those. We need the axiom of choice. You see, if you can recall, in the at the very beginning of this book, where we have set theory, the author said that in this book we are going to consider naive set theory, the set or intuitionistic set theory, the set theory where we already know what sets are, but there is another set theory which is more advanced and which addresses some of these logical issues that you run into if you are too careless. That is called Zermelo-Fraenkel choice set theory. So there you have the axiom of choice. That, however, we don't need in this book because we won't go down to that kind of depth. So these some few things like this that we encounter here and there in this book, we will just keep them like this, hanging for a later more advanced course. Okay, so that's the thing. So this result is true irrespective of the dimensionality of V. Whether it is finite dimensional or infinite dimensional, the result is true. However, we have only proved it for the finite dimensional case. Okay, now let us consider something else. I forgot to bring the ink bottle up here, so I won't take long. I will just simply mention something that comes after this. You see, if you can recall, in the previous video we said something like this: if your V is a finite dimensional vector, I hope it comes. Okay, yeah, that is enough. If V is a finite dimensional vector space, then by theorem 431 or one of its corollaries, V and V hat have the same dimension, and having the same dimension, there is a homomorphism of V onto V hat, so that they are isomorphic. Similarly, if you go one step further and consider V hat, it is called the double dual of V, the dual of the dual of V, then also there will be an isomorphism of V hat onto V double hat, which if you really write what it is, then it is this. Now there we mentioned that although these two are isomorphic, there is no natural nice isomorphism between these two. However, there is a natural nice isomorphism between these two, and for that we don't even need finite dimensionality. Okay, we can show that these two are isomorphic to each other by a very specific kind of isomorphism, and because we do not need finite dimensionality, that construction is an invariant one. Okay, and this we will see in the next video. I have to unfortunately end it here itself because I have run out of ink. Okay, this we will see in the next video, and today is Tuesday, so the next update is on Friday. So on Friday we are going to again do calculus, where of course we have started solving trigonometry, questions involving trigonometry, right? So we will continue those exercises, we will solve more of them, and in fact looking at the views, I will solve a significant amount of them, quite a few of them I will solve this next Friday. So with that I end this video. If you want to say something, you can use the comment section below, or you can mail me at my usual address. The link will be there in the description. So that being said, see you on Friday with trigonometry exercises. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.